About reduction now. Some of this you've seen before, some of it you haven't. But we've done oxidation, and now we're going to do reduction in organic chemistry. And I told you last time that oxidation, there's 4 definitions for oxidation. There's also 4 definitions for reduction. So just going to remind you that the definitions for oxidation are really increase of oxidation number, loss of electrons, gain of oxygen, simply something like carbon gaining oxygen when burning is oxidation, or loss of hydrogen, which is what we looked at just now when we were doing, for example, the oxidation of primary alcohols to aldehydes, loss of H. So reduction, therefore, is the opposite of all of those. It's a loss of oxidation number, gain of electrons, loss of oxygen, gain of hydrogen. I'm just going to put an H like that. Okay, so it kind of fits with what you've seen before. So the bit you have seen before already is that we did it as part of the reactions of alkenes. We learned already, didn't we, that we can reduce an alkene using what conditions? Discuss, tell each other. How do we reduce an alkene? How do we turn an alkene from a saturated, unsaturated alkene into a saturated alkane? Very quiet, very unconfident. What's the answer, Lauren? You've forgotten this one. No, Scarlett? No, I've done this a couple of times. Hayward?
Is it steam or admixture?
If we add steam to it, we'll make an alcohol. We add O and OH, wouldn't we? So we'd end up with OH over here. Ready?
I'm not sure.
No sure? No? Lewis? Okay, we've forgotten this. That's fine. I'm pretty sure we looked at this before. So nickel, 150 degrees. I swear that's in your notes already. I've got a nod from a couple of people. One person's nodding. 2 people are nodding. Other people are frowning. Ready? It's in there somewhere. Don't know. I'm telling you again. I'm pretty sure it's there. But we can turn unsaturated alkenes into alkanes via reduction. Okay, so this is one of the reactions of alkenes. It's an addition reaction, isn't it? You're adding something across that double bond. Okay, so that's one of them. That's one reduction. This is similar. You haven't seen this before, but it's almost exactly the same idea. So what do we call this molecule, please? Discuss with each other. You should know the names of these by now. You can spell it then, Aoife, if you don't have to spell it. Go on then, that's perfect. It is an alkyne, an alkynyl functional group. It is an alkyne homologous series. The specific alkyne is called what, given it's got 2 carbons? Monkeys eat peanut butter. It says ethane, ethene, and therefore ethine. Yeah, I think that's what you said. Near enough what you said. So that's ethine. And we can add 2 lots of H2 to it, and they're more or less the same conditions, and you'll end up with the alkane again. So we just add H2 to it twice. There is a way, those of you who go and study chemistry at university, there is a way of stopping it here, but you don't need to worry about that now. Feel free to read up on that in your undergraduate level organic chemistry textbooks if you want to. You can stop it part way, but most of the time you probably struggle to do that. Okay, so we're just adding H2 to it twice. Hopefully you can see that. These reactions you'll unfortunately have to learn. Right, so reduction then of aldehydes and ketones is completely different approach. Okay, so I'm going to do it bit by bit. I'm going to first of all show you using H what we do. So I'm just going to use First of all, you need to be really comfortable spotting reduction. So I'm going to make sure you understand that we can use this H to represent reduction. And based on what you already know, because we know how to make aldehydes via oxidation, we can probably therefore work out what the product of reduction of an aldehyde is. Right? You know how to make aldehydes from oxidation, so what would the product of reduction of an aldehyde be? Discuss. Yeah, so I'll show you again. So we know we know how to make aldehydes from oxidation. So what would happen if you reduced an aldehyde? It's exactly the opposite process. We've literally spent this morning talking about this. Isabel? You're not sure? Okay. So let me just refer you back to what we did a moment ago. You were telling me earlier on that you can make an aldehyde by oxidation of a primary alcohol. So if I were to take that, if that's oxidation, and oxidation is the reverse of reduction, what would the product of reduction of that be? An alcohol, specifically and specifically in this case, ethanol, right? Got it? That makes sense? Yeah. So ethanol goes to ethanol. There's a mistake which you might have spotted. Hopefully some of you will spot it. Where's my mistake? What's my omission? What's the issue?
You need a double bond on the... No, that much. Is it a conditions maybe?
I'm coming to that. I haven't got to that. You're right. I need to the conditions eventually. Yeah. What were you going to say?
Water.
So 2 hydrogens. This has got 1 oxygen. This has got 1 oxygen. This has got 1, 2, 3, 4 hydrogens. This has got 6 hydrogens. You're essentially adding H2 to it, but you're using a different reducing agent to H2. So well spotted. Okay, so you've got to balance these equations using these H's, even though they're kind of like representing an oxidizing agent or reducing agent. Does that make sense? Yeah. So you'd hopefully spot that, and you can do the same thing with ketones. Hopefully you can spot a ketone. What's the functional group in common with both aldehydes and ketones, please? I want you all to shout it out in 3, 2, 1. Didn't get the same answer there, so try that again. The functional group that's in common with both aldehydes and ketones in 3, 2, 1. Again. Carboxyl. Who's saying carboxyl? Whoever's saying carboxyl is saying take it to a carboxyl will get the carboxylic acid. Is that you, Hayward? Yeah, so try again, 3, 2, 1. I'm hearing carbonyl much more now, just Hayward speaking really loudly. So good, okay, fine. So we've got, it's exactly the same reaction as above. Exactly the same. What's the product here, would you say? What's the product? No? We've got 3 carbons for a start. It's propanol, but is it propan 1-ol or propan 2-ol? Yeah, it's propan 2-ol. So we're literally adding, just like we took hydrogen away from across a carbon-oxygen bond, we're doing the opposite here. We're adding hydrogen. This is the hydrogen that's been added that I put a ring around. And we do reduction. Okay, so that's reduction. The conditions for that I'm going to discuss in a bit of detail, but we use using NaBH4, using NaBH4. So we use a chemical, a reducing agent called sodium borohydride, a metal hydride. So I'm going to write a tiny bit more about that over the page, but using NaBH4. I'm afraid you're expected to know the name of this reagent. Mr. Corliss very generously spent an afternoon fiddling around with a reaction that you guys can do. You can do a reduction next year that he's worked through and TLC it. We've not got time to do it this year, but he's worked it out that we can do that nicely in a lesson one day next year, which would be nice. We'll do a bit of practicing. Did you still need that? Is that all right? Right, I think some of you have written down propan-2-ol and some of you haven't. Might be a good idea to write down propan-2-ol. The key thing is that this is a primary alcohol. This is a secondary alcohol. So you take an aldehyde and reduce it, you get primary. Take a ketone and reduce it, you get secondary. Just the opposite of what we learned before, right? Let me just show you a little bit about sodium borohydride. So sodium borohydride is a kind of ionic thing. We've got a sodium and we've got a borohydride ion. You don't really need to know much about this. I just want you to see what it is. It's the borohydride anion, BH4, and this is a source, a reducing agent. So reducing agent, source of H minus. Okay, that's kind of a bit advanced. All you need to know is it's a reducing agent. It's a very nice chemical. It's one of my favourite reactants for reasons I'll spare you, but it's usually a very quick and easy reaction to do. Works very nicely. Okay, done that. Right, yeah. So the next one is it's very similar. It's related. Just maybe make a note. This is quite a mild reducing agent. You don't really need to know that, but I want to compare it to a more harsh reducing agent that we're about to see. Okay, so we're going to do the same sort of thing now, but with under the heading reduction of carboxyls, if you like, or carboxylic acids. Sodium borohydride isn't powerful enough to reduce carboxyls or carboxylic acids. We need to use a more powerful reducing agent. This is a chemical I'm not a massive fan of, having had it explode all over my bench once before. It's not much fun. Let us just do H for now. We can work out how many H's we need. Sorry, I've written that fairly clumsily. Can you see what I've done there? Hopefully you can make that out. I might write it again actually. So now again, if we think hard about how we would make a carboxylic acid through oxidation, again we can work out what the product of this would be. So again, have a little think, feel free to discuss it. You can work this through. What must the product be? What must the product be of reduction here? Given we know how to make this from oxidation, it's just the reverse process, just like before. Again, discuss, talk to each other, have an answer ready for me. There's two possible answers, one of which I'll persuade you can't make any sense, but there's two possible reasonable answers. Magda? How would you make a carboxylic acid through oxidation? What would you make it from? We talked about how we make carboxylic acid this last lesson and this morning again. So you make a carboxylic acid through oxidation of Freddie? Or aldehyde or
alcohol.
Specifically? Well, yeah, what class of alcohol is that?
Fine.
Yeah, and you've got to avoid saying alcohol because tertiary alcohols can't be oxidised. Likewise, ketones can't be oxidised, can they? So we stop. Remember, we do secondary alcohol oxidation, we get stuck at ketone. So the two possible answers were either aldehyde or primary alcohol. Remember that pathway, Magda? We started with primary alcohol, we go to aldehyde, we go to carboxylic acids. That's what we're doing last time, isn't it? So the reduction is just the opposite processes there. Now, a few of you I heard around the room suggested that aldehyde was the product of reduction of carboxylic acids. But I told you that the reducing agent we're going to use is a very harsh reducing agent, much harsher, much stronger than the mild reducing agent which we can reduce aldehydes with. So the clue was perhaps there if you spotted it. We need quite a strong reducing agent for this, which will turn the aldehyde all the way into the primary alcohol. So we end up with the primary alcohol forming. It's not possible to stop the reduction at the aldehyde stage. If you want to make, this is actually true even quite advanced organic chemistry, you wouldn't use necessarily the reagents we're talking about here, well, I'm going to tell you about in a minute, but you have to convert, if you want to make an aldehyde, you convert a carboxylic acid to a primary alcohol, then you then convert it back up to an aldehyde again. There's ways of doing that. Right, so let's think about this. This is not balanced now, is it? This is not a balanced reaction. So we've got to think about what the byproduct's going to be, which you can guess based on what I told you before, and then how many hydrogens, or how many H's in square brackets we need. So think about that for a moment and discuss. What's the other product, and how many H's are we going to need? Zara, what's the other product? It is water. Yeah, well done. So you get water byproduct here. If ever you're in doubt in chemistry and you're thinking there's another product, always try water. And how many hydrogens then do we need here to make it balanced? Do you want to count and check? Okay, let's count and check. So how many hydrogens are there on the right hand side? Yeah, you need four. You need four H's, don't you? Because I think what you did there is you forgot the water. So two of the hydrogens are required to, if you like, steal the oxygen away to turn it into water, and the other two hydrogens are needed to kind of stick to the hydrogen, to the carbon, right? So that's why we need four hydrogens there. The chemical we use for that is something called lithium aluminium hydride. So lithium, another metal hydride. And again, it's a bit like, it's very similar looking if you see what I'm doing here. And you don't need to be able to draw this, it's just for comparison and interest really. It's a metal hydride again. Look how similar it is structurally to sodium borohydride. Very, very similar sort of idea. Again, it's a metal hydride reducing agent, a source of H-, just like the sodium borohydride was. You're expected to know that you would do that. Has anyone got the revision guide on them? I just want to check what you need to know. I'm pretty sure you need to know this, but I don't want to tell you stuff you don't need. You got it on you? You just turn to that page. I'll write it down now. If you just turn to that page, reduction of carboxylic acids. Do you need to know this is done in dry ether? And then there's a second follow-up step as well. Let's have a quick look. Just make sure we get this right. You don't need to know the conditions, which is nice. You don't need to know the conditions for that. We go. So that's that. You need to do it in dry ether. If you want to know dry ether, then then acid, but you don't need to know. All you need to know is lithium aluminum hydride. That's it. Okay, there we are. So that's reductions, and we'll do practical using sodium borohydride in the new year. And so I'm just going to stop that there. And I'm going to do a little bit on nucleophilics to change gear completely now. This is a set. I'm going to bash through this fairly quickly because this is something we're going to do in quite a lot of detail next year. So it's just I want to cover the standard course properly. But I'm going to come back to nucleophilic substitution in some detail next year. So don't worry too much at this stage. It's quite a lot to come. You'll spend a lot of time on this next year. Right. So the term electrophile we covered before, right? We covered the term electrophile, didn't we? Electrophile is a what? So phile, lover of, or liker of. What's it like? What does it love? Electrons, negative charges. So nucleophiles love positive charges, right? So like negative charges and are therefore positively charged or partially positively charged. Nucleophiles like positive charges and therefore are negatively charged or slightly negatively charged at least. Okay, so this is nucleophilic substitution. Substitution is swapping one thing for another, and it does it so nucleophiles, this is straight from the spec, from the spec, sorry. Nucleophile reacts by donating both bonding electrons. Sorry, I can't squeeze that in. Nucleophiles react by donating both bonding electrons. You're expected to, for standard level, recognise nucleophiles and be able to write the reaction. But the mechanisms and whatnot we'll do in so much detail next year, it will be very easy. Okay. Okay. Right, so an example of this then would be something like this molecule. What would you call that, please? Tell each other, what would you call this? 3, 2, well, go on, Tom. It is an halogenoalkane, good. So, yeah, bromo what? How many carbons has it got? Right, so bromo ethane or ene or ine? Is it got a double bond? So, yeah, so bromo ethane, and that would react with a nucleophile would be something like a hydroxide, which is a nucleophile because it's negatively charged, right? That's what you expected to spot. Nucleophile, negatively charged. Did I say positively charged? Anyway, nucleophile as negatively charged. And it's going to provide the electrons that make the covalent bond in the product that I'll show you in a second. Okay, and the bromine here is lost, or Br is lost, right? So it's a substitution. So the Br is lost. The hydroxide becomes a hydroxyl, and the bromine that was part of the halogenoalkane has become a bromide. Overall, it's balanced, isn't it? Because we had a negatively charged reactant nucleophile, and we end up with a negatively charged leaving group. We call these things. This is the thing that's lost, leaving group. So it's a substitution. Think of it like football if you want to. We've got Harry Kane there playing okay, and then subbed out once he's got cramp in extra time. He's left over there. Okay. Okay. The chemical you might use for that might be KOH or NaOH, but I've written it as an ionic equation, haven't I? I've not bothered writing the K or the Na because they're not participating in the reaction. And this is something I'll spend a lot more time, as I said, next year, and I'll include, people get all excited about seeing the potassium and sodium and think they're part of the reaction. In organic chemistry, quite often we ignore the things that aren't involved. So we write them like this, but the stuff you chuck into but you can't get a pot of hydroxide. You have to have a pot of sodium hydroxide. The sodium's not doing anything apart from keeping the hydroxide company or the bromide company at the end. All right, so that's all it's doing. Right, so that's that. I'm not even going to bother teaching you the simplified mechanism, which is in the slides that I'll share with you, because I'm going to do it in so much detail next year. Right. That's all I'm going to do on that. There is more. There's examples of that, but they're all the same as each other. Let's do an example. Another example. See if you can work out what the products are. Hopefully this won't throw you off too much. So first of all, I want you to tell me the name of this chemical. Tell me whether it's primary, tertiary, or secondary. And I am going to write this time sodium. More like to use potassium. This potassium hydroxide. What are the two products, please? What's the name of this product? Name of the reactant, name of the product, and draw them. Okay. So you can do this reaction with primary and secondary and tertiary. It works exactly the same. Well, the mechanism's different, but it's, as far as you're concerned at the moment, the same. I'm going to stop the video at this point. I'll write the product down first. Looks like a few confident answers around the room. Lauren, feeling confident? Do you know what the product is? Have you worked out what the product would be, even if you don't know the name of it? Yeah, so we've got one of the products is Cl minus. Okay, but okay, go on. Yeah, the Cl, so it's the same. Looks the reactant and the product look the same, apart from, whoops, the Cl has been replaced with a hydroxyl. And you said it was Cl minus is the product, but look at the reactant here this time. We've got the K keeping it company. So it's KCl, yeah. What's the name of this then? So what's the longest carbon chain? So it's propane. Yeah, so it's going to finish propane, isn't it? And we're going to number the carbons 1, 2, 3. It's 2-chloropropane would have an H there. This is a tertiary halogen alkene, isn't it? So it's 2-chloro. What's this? Help her out. Help her out, folks. 2-methyl. 2-chloro. 2-methyl propane. Let's refresh from what we did a little while ago. And what's the name of this stuff? Please, Gregor.
2-methyl propane
2-methyl propan 2-ol. Yeah, so just a refresher of the names. We spent a lot of time practicing those before, but it goes, doesn't it? It goes very quickly. So a little reminder there. Now I'm going to stop the video and give you a little challenge.